Okay, hello. So today I'm working on the same virtual machine I've been working on for a little while. I added a feature called quotations to the assembler, which is something that a lot of the modern day concatenative forth-like languages use, like factor and retroforth and a bunch of them. And it's a way of basically creating a function, like a lambda function, an anonymous function on the fly. So if this works, we should be able to say something like, I'm going to define a named function, or call this A, right? And in here we will add like 1, load the byte 01, load the byte 2, just to have something on the stack, just for something to do. And then we're going to add this new or macro, I guess. And what it's going to do is it's basically recording wherever this gets assembled. It's being recorded, and then we're going to say plus add, right? And we need to return from that function. So that's a nested function, and that's the closer for the operation. And then we will return from this function A. And so when I do that, rather than adding them, what it's going to do is it's going to put the address of this function on the stack. So when I call that with Control A or invoke A, so we have 1, 2, and then we have 38F, which is the address of. So if we say, what is that, 38F? We should see that code. So it's actually pointing to this spot. Hello, whoever came in, welcome. So it's actually, basically this recorded a pointer to this, and then what you're seeing here is so after the return, it says load this address, which spans these 4 bytes, is that same number right here, or it's actually right before that. Or no, it's actually it's what put this on the stack. So that's the unfortunate encoding of the number 38F, and disassembled it. It doesn't know that it's a number and not like opcodes. So anyway, so basically this function, like the address of this anonymous function, is on the stack, and so now I need to be able to invoke it. And there is not a like direct way to do that, but it's actually pretty easy. So we need to define another like operation or whatever, what I'm going to call X for execute. And what it does, when you call this function, what it's going to do is pop. It's going to take the normally when you call a function. Wait, am I doing this right? No. What it's going to do, I want to take this number and push it onto the return stack. And so I'm going to take it off the normal stack. I'm going to take it from the data, move it to the control stack, and then I'm going to return. And that is going to cause the return to go to that function. So like basically this is a hack that kind of like destroys the natural order of things, or subverts the natural order. So when I do that, and I press or I type in this to execute it, it will execute this function. And so what it's going to do, it's going to take the address here and jump there. And so and then it should add these 2 numbers together. So what I would expect to happen, fingers crossed, right, is to see the number 3 on the stack, and all this other stuff will go away. There we go. All right, so that's what quotations are. And so now that gives us a way to create a function on the fly and pass it around to other parameters or to other functions and that kind of thing. And that style of programming is called a combinatorial programming, I guess. And it's kind of neat. But it's the way that I like to do parsers. I have a parser combinator library that I've written in numerous languages. I did a stream. I wrote it a long time ago. What am I doing? I wrote it a long time ago in J, which is a little cryptic language that some people who are familiar with my channels might know, but many people will not. And then I ported that in another stream along about a year ago to JavaScript, and I want to do the same thing for assembly language, for this assembly language. So it's a little bit complicated because I don't have a way to like allocate arbitrary data structures and refer to things by name like this. It's a little bit harder. So for example, the main operator is called sequence, which is defined here. And you see it's kind of a for loop. It's like, ideally you want to pass in like a list of things to do, like a list of things that can match. Like we're going to define a grammar, right? Like I guess I want to define this. I want to parse like a number, for example. So that's a digit. So it's one of the letters 0 through 9, and then we'll call that a digit. And then we'll say I particularly want to do hex. So hex it would be A F, like in quotes or whatever. These are characters. And then a number would be the negative sign, which is optional, and these are only integers. So followed by this combinator this, I think of it as a combinator, but this operator means preceding is optional, and then any number of digits. So we could say digit or hexit, or actually we could say digit hexit is like a digit or A through F, and then we can just say hexit. And there must be more than one of them. And then that's it. So we have this combinator that means like, multiple, repeat. I call that rep. I call this one opt, for optional. And I call this alt. And then they're all sequences. Actually, this one is like I think it's any is the. Okay, so this is what I want to write, and then that's going to wind up looking something like I think I call it char, or what do I call it? Doesn't really matter what you call it, but I try to keep them consistent. Set. Choose, right? CHS for character set or choose, depending on how you want to. So character set, and I would just type in the numbers directly. 5, 6, 7, 8, 9. Oh, this is B. And then again, A, B, C, D, E, F, A, B, C, D, E, F. And so maybe digit is this, exit is this. Num going to be the character negative sign and then opt. And maybe we'll call this char. Something like that. Opt, and then hexit, and then rep, right? So really, it's this. We're gonna do it like something like that. I think it's gonna look like this. So load byte, that thing, and then chr will be there, and then actually this might have to be in quotes too. I think this is going to have to be in quotes. That's going to have to be in quotes. So it's like it should be like this, this. I'm just making this up as I go along. Then we call hex it, and then we call, right, so that's in a quote, and that's and then this one should be digit 4. And so we have to act, this is actually going to be a word that we implement. I might write it like this. Whatever. Return. So this will be a quote. It'll actually be a string. Choose, right? And then return. And then this would be exit. Is that okay? And then rep. I think that's what I want to write. I think this is the code I want to write. Oh, except this would be would also be, sorry, that would have a dot in front of it. This has a dot in front of it. Go this way. And here we would say close that too, don't we? Let me think. Do I have to quote that part? No, because this is an argument to the choice. This is the argument to the choice. Like so this is that you can actually implement like this thing in terms of this operator. So this is like the fundamental thing, but I like to do this as like when it's a set of simple character matches, and I like to put it in. So I think this is the code I'm going to write. So I'm going to write code I want to write to match a number, a hex number, and then call this BBNF code, BBNF grammar for a hex number. I'm going to put that in comments. Okay, so if I need to define choose CHS return. I need to define type. I don't know if the assembler is going to let me do that. I think it should, but I'm not. Well, I guess we'll find out. We can try right now. Hello, or and then if I should do like this, 1, 2, 3 return, but I can't do it like that. C1, C2 return, constant 1, constant 2 return, and then if I call that, it should put 1 and 2 on the stack. So it should say 3. Oh, clean that up. So it'll say 1, 2 if it works. Oop, does not work. Underflow. Why? Okay, well, I'm not going to try and debug that right now. Let me try it one more time. I'm going to say C0, C1, add return, and that should put a 3 on the stack. And I call it, right, because 0 plus 1 is 1, not 3. But that okay, so that actually did work. I don't know what one. So this works. So I can use that character. Answers that question. And then oh, actually, you know what? I can give these I can give them the cool names. But that would be a plus sign, because in b4 I use like instead of multiplication I say ml and at. These are the primitive operations, so I actually can use the syntax I want to use. So we can say return for that, and we can say question mark for that, and then we can do this, which is so this is called opt. It's called rep, what I call them, and I call this one orp because it's an optional repeat. and this one is called halt. And then usually I have one called seq, SEQ, that is a sequence of things. But as I said, I don't like it's tricky to like ideally what you want is like a pointer to this whole thing, but that means you have to like compile it, remember where the address was, and then like compile the address, and then you can have like an array of like just pure function pointers. But that's very, very hard to do in a Forth-like language, and especially in an assembler when you don't have like dynamically allocated memory where you can like put something in a buffer and then keep it around for later. So this inline style is really, really neat. All it's really doing, I can show you the code. It's like 2 lines of code. So in pass b4asm. Kind of messy, but I added these 2 things. So this is inside the case where we have a dot. Then we have token tag is open bracket and close bracket. So if I search for OB again, all it's doing is it's compiling. So as soon as you type inside the colon starts the assembler, and then inside now you're assembling and you're coding these. You're putting these things in memory, and so this, all it's going to do is it's going to compile or assemble a hop instruction and leave a blank, which is what hop slot does, which is some function that does that. And then it's also going to remember, like in the assembler, it remembers the address of where you started, and then you put all your stuff in there, and then at the end, when it sees the close bracket, what it's going to do is it's going to make a copy of that address that it's remembered from way over here, and then it calls hop here, which goes back to that address and tells how far to hop. Yep. Hi, Harmonica Muse. Yeah, I'm making this up as I go along. Although actually, there is kind of a reference here, which I could put in the chat. Yeah, I will not. But it is. This is something I'll get to in a minute. But github.com tangent storm syndir syntax directed something. It was supposed to be an editor. There's not really much of an editor here, but there is in this file a something called parse code. I'll put that in the chat. And nobody knows enough about b4. Not even me. I'm making up as I go along. But thank you for watching. How do I chat? My window is not big enough to. There it is. So as the J combinators, and probably you can't see the one because I stuck it in a private repository. But github.com tangent code platform, something I've been working on for a while that you cannot see because it's a private repository. But if I go into here, I go into JS. Parsecode.js. Oh, 9 months ago. So I will take this, put all this, just.github.com, parse code, yes. And then I will add the test suites there as well, so you can just parse code test. I did this all in a live stream a while back, the JavaScript version. This was all live coded, I guess about 9 months ago. And then the tests. I'm looking for the button to add a file, or to even just to edit this. Edit. This does not appear to be JavaScript. I think it was just notes that I was taking so that I could use it. I was just doing this interactively. But you can see that, like, this is kind of like the state of the parser. So like there's the MK. This is index. There's the character that you're looking at. This is the index into the string that you're parsing. The input buffer, then the match bit. I have no idea what MK is. Oh, mark. It's the start of the token. -1 here, I guess. Okay. Anyway. Oh, I was going to put that here, and then JavaScript version. Yes, version of the parser combinator. Okay. So we got those. We got those. I'll leave those up just in case. And then this is. Oh. Hey, Kyle. Yeah. So I don't usually post. I don't know where you saw, but I don't usually post these things. Kind of just do them whenever I have a chance because I don't really have a schedule that I can keep to. But I thought this one was going to be fun, so I posted it to a lot of places. All right, well, we'll try it, but let's see. I'm kind of gonna use those as a guide and go down the list. It's really meant to be like a trail that like I or anyone can follow, and eventually it's going to be like a series of challenge responses that like this whole thing is like a course. I'm slowly kind of trying to follow, make a trail so that and leaving these tests or whatever as breadcrumb. In fact, I can use these exact tests, I guess, and try to make that same set of tests or same set of I don't even know what I'm trying to say anymore. All right, so I guess what I was going to say is like so the one thing that's not here is sequence, and as I was saying that you can't like in all the other versions I just create an array and it has like a number or something in there, maybe even like some complex object saying what needs to be done, and you just loop through that array to match a sequence. For example, this is a sequence. You have a digit followed by, or sorry, no, this is a sequence. You have an optional thing followed by some number of things. So the sequence is negative sign and then whatever. This thing is one combination, or is one. This first line is one thing in the sequence. This is the next thing in the sequence, and so the whole like definition here is a sequence. And so I think that's the way to do it in Forth. That seems to be a decent way to do it in Forth, going by that article that I was just looking at here. Compiler design has nothing to do with this, related to this topic, but nothing. Conversation. You just happened to mention that book, and I realized I'd never read it. Dragon book. Okay, so a BNF parser in Forth. I'm just going to go over this just a little bit and just review what I've learned. So this is by Bradford Rodriguez at bradrodriguez.com. So, and this I found this years ago. So, Sigforth is something that came out. It was popular in the 80s, 90s, and whatever. I guess he's still around, but he kept this up there. And this is like in traditional language called Figforth, very popular. You can see it. I guess it does have lowercase letters, but like the actual language doesn't have lowercase letters. It's a neat language. Got in 1988. All right. Well, we'll see. So he's just talking about what BNF is. So BNF is a simpler version of what I'm writing. This is what you would call extended BNF. Niklaus Wirth wrote, made this up, and it adds the the question mark and the plus and the star. Although he didn't use that notation, those came from a guy named Claney. Might have seen them in regular expressions or whatever. But the the E is for extended because BNF does not have repetition. It doesn't have anything except sequence and alternation. So those are kind of like the two core ones, and from that you can have anything else. You can generate anything. Okay, so this is just saying what it is. This says simple solution through conditional execution. So what he did is he started with the idea of keeping a flag on the stack. So what this says, he's defining this word. So colon defines a word just like in my language, although I don't have a space. Is the name, the word is pipe or whatever you want to call it. And then it looks at the top of the stack, so that's if. And I like to pronounce that if so, right? Because I think of it as if condition, then do something else, and then end. But in fourth, you say condition if, do the thing, and then, right? And so I prefer to pronounce this if so. So you look at the test, you say if so, then what you're going to do is take the return address off the stack. Is that true? Yes, right. So you're in the middle of executing. Like this is more code down here. You're in the middle of executing this. Well, this is not actually code, right? You have to say BNF or something like that. But imagine you're trying to go through this list and you see it matches 0. So then when you don't want to test all the rest of them because you've already matched a digit, right? You match 0. So what you want to do is you're going to put a match bit, the bit 1 on the stack, and if so, you want to exit out of this function. So what normally happens is you go to the end of it and then you call return. Right? Because the return address, whoever called this function, its return address is on the control stack. And so you would call this is a function, right? So, or procedure, right? You're calling this procedure. So now the return address on the control stack is the address of this 1, right? Again, this is not the right. This is not actually fourth code, but hypothetical. But and then you're going to call this again, and then the return address will be the address of this 2, and so on. But then on the return stack, after the address of this 1 is the address of wherever you would go, like in this number 1 here. Like it might be this operator or this operator, because you're calling digit at the moment, and so the return address is here. And then when you call this, there's another return address that's going to put you back here, and so this thing takes the thing off the control stack, takes it to the regular stack, the data stack, and then just gets rid of it, and it puts a 1 on there. So then is the end of the condition, and then this semicolon returns. So when it returns, it would have normally gone back here, but we took that address off the stack and destroyed it, so it doesn't remember that it has to go back here, and instead it's going to jump back out here. And so that is the short-circuiting behavior. And so that, I think, is going to be fairly easy to implement. We can just port that word absolutely directly, except I'll port it exactly as it is for now. So I write .i for it. I'll copy and paste it. So I'm calling it I called it single pipe, and then instead of if I say .i, and instead of r I say control to data, and instead of drop I say zap, instead of 1 I say c1, a constant 1, or you can say lb01, load byte 01, but I'm gonna say c1, and .t for then, and then the return is the return. This is the exact same code, same logic, just different syntax. And I believe that should work for us. But we don't have a match bit yet, and we're going to do what he does in a minute. And right, so alt, and it takes, well, I'll draw a stack diagram. It takes a match bit, so we'll call it M, and well, whatever. And it returns a match bit, a new match bit, right? In fact, it returns the same match bit. Right, because if it has a 1 on the stack, so the if or the .i consumes the whatever's on the stack. So if there's a 1 on the stack, then it's going to pop the return address and destroy it. So basically it's doing like a double return. And then it's going to put a 1 back on the thing. And if it's a 0, maybe in this language, I don't know. I would expect it to have to put. I'm going to have to put another 0 on the stack. So I have to put an else because the if consumes it. So I would think I would have to put a 0 back on it. We'll see. Maybe I don't, but I would think I would have to put the 0 back there. You say if else then, which is weird order. That's why I say if so. Yeah, because it has to have a bit on the stack. So my guess is that if does not. Why wouldn't it drop to 0 though? Yeah, I have no idea. I would expect this to need an else, but beats me. Maybe I'm just not thinking clearly about it. Oh, Uxental. So I've been looking at Uxen. I don't know if it's Uxen or UXN. I think it's really neat. The ecosystem that they have. Another virtual machine like this. Might ask why I don't just use it, but there are lots of projects like this. I just wanted to try my hand at making my own. And I said, like, as I said, like, leave a trail. That's part of the goal here, is to make this like a course that someone else can follow, like step by step. Eventually. Okay. So I think this has to be there. I can't explain why this is not there in the other code, but I believe it has to be there for mine. All right, so that's basically how this works. The and works the same way, except it's it flips the bit. But he abandons this method, and so the reasons that he specifically abandons this. The reason is, let's see, we need an explicit operator for concatenation, which he doesn't like, and I don't like. They have equal precedence, which is also true. You can't mix them in the same word. And I didn't think about that, but we have to make. We've made no provisions for restoring the scan pointers. We haven't gotten to actually matching anything. All right, so the better solution is. I should post this too. I want to follow along. Paper. All right, so consider a series of terms, 1, 2, 3. Execute normally, return false. The 2 is entered and exits immediately, doing nothing. So the idea is, yeah, so where does it say it? Yeah. So if false, the word exits immediately with false on the stack. Otherwise, it parses and returns a true value, a success value. So, like, we need to give a name to that. I don't know what he calls it. I think that's implicitly compiled by his BNF word. Did I say what B and F was? Backus Nor form by John Backus and Peter Nor. Nar. Yeah, and then okay, so that gives you the ability to put this in. So it's a really nice way of doing that. And then backtracking, we'll put the pointer on the stack, basically. The character pointer, we'll save it. This is a variable, and he doesn't use the stack anymore, so he moves it to a variable called success, which I'm going to call M for the match bit. So here we say at M, and then instead of C1, we're going to say, we are going to say C1, we're going to put it in, oh, I see now. We're going to write it We're gonna write it, but you don't have to write it because it's already 1, right? So if it's 1, then leave it at 1, and if it's 0, leave it at 0, and so there's nothing to do. So I suspect that's why he didn't have, because he didn't actually use this code. This was, so I bet it was not tested, and he just forgot that he had to put the 0 there, or maybe if leaves a 0 if it's a 0. I don't know. Maybe it's the end of a loop or something. So I think this should work now. So okay, so now I should compile this, right? I should assemble this. So what you're seeing down here is the BIOS, and it lets me say, like, if I make a string, I can say put S, and it writes it to the string, to this table. And I do plan to use that at some point, but for now, let's get rid of it so that we can. I can't actually like page through this at the moment, which is silly. I should have done that ages ago, but let's go ahead and assemble this code. So on the command line, or in here, you can ask it to assemble something on the fly, but I just do it here so we have a starting point. I'm calling this pre because it's a before pun, and also because it's parsing in regular expressions. So pre. Oh, unknown word colon. I mean, what? But I just what? I think it's blowing up on this definition because I'm using that word. But I thought, well, okay, that's true. There is no character word. Unknown word. Oh, okay, so I can't use this. That's too bad. That's a bug. I'm gonna just add a note to myself to my plan that says inbox to bug that cannot somehow like can define interactively but not with -a. So I don't know why that's the case. So I'm just gonna call this alt opt rep. Or maybe you can define it, but you can't can define but not call it, but not assemble it. So there's something wrong there. So I'm just going to call them, or I'll give them the names. So I'll call this opt, and I'll put this question mark here, rep, and plus warp optional repeat, or the claiming star. Clean star, but I said his name was Cleany. Kalene. He like one of the guys that help pioneer the work on regular expressions. Okay, so then we have to change these to alt. That's actually really annoying because like you want something like this. Like, maybe I could do. Unknown word, even one of them, okay? What about, I do like, just give it, I just want to see that, like, visually, I like the pipe character. Nope. Oh, okay, it actually took that. Huh. I don't know why. I give it a dot. I don't like that so much because the dot is meant to indicate a macro, and this is not a macro. Yeah, unknown macro. Yeah, okay. I'll put an O in front of it, so it's an op. How about that? Yeah, okay, it allowed that. Let's do O question mark O rep and O star. And then eventually I will fix that bug. See if that works. Okay. And so now the BIOS is not there, so this is what got assembled here. Real pretty, right? So you can see there's the return, and then there's the @m and the HO, the hop. There's a hop created by the if. There's the CD. This tells you how much to hop. I guess 4 characters. 0, A, B, 5 characters. E zap return. Oh yeah, the return is from the top. Then does not emit anything. It only tells if where to jump. Goes back and it says how far to jump. That should be 2 though. Why is it 4? It's 5. Why is it 5? There's only two things here. I mean, I don't know. I know it works, so this must be the right thing, but I would have expected that to be like jump forward 2. I can't explain that. Maybe it doesn't. Maybe it's including these operations themselves. I forget why it does that. That's a little weird to me, but I guess that's how I designed it. So. Okay. All right. So just to test that, how would we test that? I guess we could do this. We could say, we'll call it. We'll just call it A for thing to do. G for our grammar, right? And we'll say put a 0 on the stack, and then, or let's see, 0 on the stack. How about we say the 0 on the stack, set M to that, put a 0 on the stack, and then call the operator. And then we'll put a 2 on the stack so you can see it. So put a 2 on the stack, call this operator, and then put a 4 on the stack and return. And I think what's going to happen is we're going to see 2 and 4. Okay, that's what I would expect to happen. 2 and 4, yes. So they're down there. You can zap those. And now let's do it again, but this time we'll put a 1 on the stack, or into the match. And so now this time it should say 2, and not do the 4. And so that this should cause it to short circuit. And there we go. Okay, so this is working. All right, so I don't have tests for this, but let's call it pre-test.org. And I'm just, again, trying to leave a trail. So source b4a, and we'll make this a test. So our first operator will be the alt operator. Okay, so and I'm not going to like type all this out right now. But so this is our input, and then I'll Control G. And then we will ask for the stack. So we will ask it to print the stack. But we ask the debugger to print this. If you type $D, it prints this line down here. That's what's on. And then that should be 2, 4. And then if we do it again, it should just be 2. Right, so I will call this implement the operator alt. And I'm going to put it to do. As in every one of my tests, it says to do fix this dumb bug. And basically, the test runner skips the first test. So fail, fail, fail. This gets skipped. Okay. And then I'm going to. I'm just going to write a little test files. And I'm going to write test.read. And probably don't need to remake the interpreter each time, so I will say enco run pass pre-tests, and we will run pre. I go another shell, and I run test pre. It's mad because it doesn't see a name. I didn't read that. I'm guessing that's alt pre.alt, and then skip me ankle bug. Okay, it's just mad about something else. No such file or directory pretest. Okay, because that's in the BIOS directory. Write it to test. I've also considered calling this prex. That's what I usually call it, prex. b4 and run it again. Okay, and it fails. Oh, because I didn't clear the stack. So the stack still had the 2424 on it, and it wants to have a 2. But it also put the 4 on it, so this didn't work because I didn't define what. Oh, and I didn't change this to 1. That's why. So let's say zap zap. I guess we now have I think it's R to reset the stack. Army. How about capital R? There we go. So the test pass. Okay, so we can close this. We can switch over to his. Should have made this big. And okay. Okay, so we'll make that the first op. And then, yeah, so like alt and seek. That's alt. Sequence is just, what would you call this? Execution. It's just normal b4 execution. And I'm going to put a link to this paper in here as well. Chat already, but I'll put it in this file for your readers of the file. So inspired by. This is also inspired by, if I'm going to cite my sources, this would be Omega 2 paper. I think it's on tinlizzy.com. Yeah, this guy. That's not the one. By the Tin Lizzy guy, but it's not this point. It's not the viewpoint. You worked with Alan Kay for a while, and they were doing a similar kind of thing of trying to like leave a trail of they call it steps of starting from like a tiny virtual machine and working their way up to oh, it's not Omega 2. It's no, it is Omega 2. Yeah, this is oh, okay. So that link is dead. But this is also that's unfortunate. It was yeah. Got redirected back to a site anyway. That's weird. It's back on Tin Lizzy. Okay, so chapter 2 of this, in which he defines all these parser combinations. So they're a peg grammar, but he has a really nice little like there are many implementations of parsing combinators and whatnot. I'm not sure he even uses combinators here, but he does use rules or whatever. Somewhere he has like a really nice sequent diagram, like the inference rules. Like it's these, but it's one diagram. Oh, maybe they're just scattered throughout. And so we're combining these two approaches because Rodriguez did not use and first of all, it's only BNF and it's also doesn't combinatory approach. Okay, inspired by combinator inspiration. My hex dump. Oh yeah, thanks. Yeah, I like the. You've always been able to do that, but recently I've been making this little shell, and it just makes it so much nicer. I really need to have the ability to like roll through it. Like there is a version of this in Decker. Oh, I screwed up my tangent form. Oh, where does it? B4, right? In the B4 repository on GitHub, there's a Decker version. I think it's on the site. It's probably online. Let me look at the. Oh, I was in the wrong. Oh, so if anyone doesn't know, there's a site on Discord. There's a concatenative server. I don't have the link. Yeah, I do have a link. I don't know how to get a link out of here. But they were kind enough to give me a channel for B4, and so I post there instead of on stuff. And this right here, B4, is a okay. Well, yeah, you got to scale it a little bit because I designed it weird way. But there's an online interpreter that you can use to play with this. And why was I saying all this? Oh, because it has a description of the system, but oh, this is old. My font editor. I forgot I had this. I just re-implemented this basic thing. The pixel editor. Oh, maybe it's not a pixel editor. Browser. I made a pixel editor. Yeah, in the latest version of this is scrollable. And it's got like a little scroll bar here, and you can scroll up and down. I'll have to update this file. And probably, like, I've got a website for B4. I just haven't put anything up there, but eventually that's going to be up there, and there'll be like a whole little course. All right, I'm rambling. That was all about the hex stuff. Okay, enough of that. This is also up here as a view of memory. It's a view of a screen. It renders it as text. If the BIOS were installed, you could put it right up there. But I think you can also just say, just assemble something directly there, like hello world. Except you can't do that. You do a string hello world. That should go. Yeah. Oh, unterminated string literal. Huh. I'm not sure what's causing that. All right, that's another bug to worry about later. No idea what's up. But anyway, you can just write directly to video memory. Oh, you don't understand what @m means. So there are 32. Let me bring up that thing again. There are 32 registers in this virtual machine, and they are given the names @ through they're given the name @ through underscore, which these are the if you look at the ASCII character chart, first 32 characters have these exact names. So Control A, Control B, starting with Control @. And so I use them as registers, and they have 4 associated opcodes with them. This is, so Forth usually has 2 stacks and a dictionary. So I have 2 stacks, and I want a dictionary, but it's an assembly language, so the registers themselves are the dictionary. This is a dictionary that is like dynamically is assignable. So they are variables, but you can do 4 things with them. You can invoke them. So okay. So here I assembled something to memory address 600, and if I just turn on the assembler, I can. I actually want to start at like 180 right here, 180, and then I want to put like I'm going to have the assembler put something in register. First of all, let's look at what's in register A. Nothing, and then I'm going to assemble something. And we're already starting at this address 180 down here. So I'm gonna write hello again. And so now this is the length of that string, and then the letters are there. And if I do A again, it should say 180. But it doesn't, because I didn't actually tell it to assemble something named A. All right, so do that again. I'm just going to overwrite it, and I will change this. I'll put an exclamation point there. You'll see this change, and you'll see another character show up here. There. And so I've associated this address 180 with the address like the assembler stored that in register A. I think I can say, is it R to show the registers? No. R, no. You got, I have help. I had something, I forget what it was. Oh, to show the ops. But you can't see it because the screen is too small. How about for I? No, that's not what I want. Maybe I don't have something to just dump the registers. Maybe I should. Maybe it should be down here. Like anyway, but you can look at what's in the register and you can see it's 180. I thought I had a command to show them. All this is doing is showing the opcodes. Say b4 for I. b4i is the version of this that does not have the all the fancy REPL or whatever. You can do the same thing, and you can say \o, and you get this chart of the. Thanks. So the reason for this. Oh, anyway, so then in invoke you can inspect. You can see what's in there. That puts it on the takes the value out, puts it on the stack. This takes a value on the stack, puts it in there, and then these are like hoop counter kind of things. So they take a value off the stack, add it to the value in the register, and then return old value. But I'm thinking about turning it to the new value. And the idea, the kind of overarching idea behind this, is that if I call it IO byte, I call it public bytecode now. But if you look at the way the UTF-8 protocol works, like all of these things are they're printable ASCII characters, and then these red ones are prefixes that say these bytes, the following bytes are going to be like a multi-byte sequence, and that's how you get like multiple, so many languages. Like ASCII is always one byte, but anything else has multiple bytes, and so these C2 through F4 are intended to be you're intended to be able to like take text and stream it into this machine one byte at a time, and what these do is they do the same calculations that UTF-8 does, and put something on the stack. They put the code point that they build up the code point that you want on the stack. Well, these right here are never the first character of a UTF-8 sequence. They're always it's a weird thing. It's like take a number, like all of these things mean take some number, multiply it by some power of 2, and then add the next one. So you'll have like, they're not color coded, but some of them are like 5-byte sequences. I think these are 4-byte sequences. These would encode like 5 and 6-byte sequences, but the Unicode consortium decided they would never do that. And then some of these on this row are like the 3-byte sequences too. So you have like a cascade of these things, and then eventually you get to these, which like add a number to whatever number you calculated so far, and so that gives you the last little bit of it. And so these are never the first character of a sequence, and because of that, they're free to be used as like the operations internally. And so I think of this as like a calculator where you can press these buttons to make it invoke things you've defined. Invoke these buttons to do the things that every B4 system does. These would be like specific to that particular device. Like if it's a microcontroller, they're features of that particular machine. These are the generic ones, and then these are the ones that are grayed out are designed for you to make it extensible. In fact, the green ones are not even used either, so that they're all extensible. Actually, this has changed to C0 and C1. The hex codes C0 and C1 are here, and I thought it made sense to make them constants. And I forgot and made C2 and -1 and C4, and then they're not valid. You can't make them ops because they're Unicode. Yeah, I'm rambling. Anyway, that's the VM. Okay, thank you for complimenting it and then listening to me ramble. Okay, let's get back to this. So, inspired by all that above, so seek is just normal before execution. Alt is an early exit. We use at M for the match bit. So this is the signature is actually wrong. It takes nothing and returns nothing. It is stored in M. Match bit is stored. Okay. And that's taken directly from the other paper. Okay. So what do we want to do? I guess we should let's put this back in. I'm thinking of using the following registers. So in the BIOS, I started using K as okay. So like kind of this is what I'm thinking. Like so the like all of these invoke something directly. The @ sign, which is op0, cannot invoke directly because I wanted 0 to be a no op. But what happens is that whatever address is in there gets invoked whenever you press a different letter. So if it sees a K, then it's like the character handle. But all the rest of these are free for any use on any individual machine, but the BIOS is picking some of them. So the convention I'm trying to follow is that A, B, C, D, E, F, G, H, and H are like registers. So if you want to write a compiler, that can be your stack frame, you know, with your arguments and local variables. I and J are loop counters, and then K, like basically K through maybe T, I'm reserving for use in the BIOS. And so K is my character pointer. K for sounds a little bit like character. So if you have an input, wherever some input buffer in the world is, K is pointing to that. And so I'm reusing that same concept to be the character pointer. So yes, I'm not sure what I need to do with that yet. Other than note that that's what the plan is. Then M is going to be the match bit. Oh, like outputs a character to that terminal. What else? Well, I guess so. I guess what we need is ch. All right, so here's the next test: is current character. In fact, I think I put this in the BIOS yesterday. I started, so off camera. I've been working on a little like Lisp interpreter in this thing, and I wanted a parser. Why is this? Oh, that's this is the BIOS. I want oh, I was looking to see if it had the word in it. Yeah, so I started adding this in here. So I created an input buffer at the start. K is pointing at the start of the input buffer if you load the BIOS, which I have not. We explicitly did not do that. Maybe what I'll do, you know, this is funny. I'm gonna hang on a second. The BIOS mini BIOS hack. Mini BIOS hack. Normally you start assembling at position 100, which is 100. I'm going to put that there, or I'm sorry, 256. And these are all hex numbers. And then I'm going to put this, put input buffer in video RAM at start of video, at start of video RAM. And so if I put 600 here, or 600, that should compile this to the video RAM. And so now it won't be taking it. Oh, what happened? Cannot create the executable because why? Because it's running? Because this is running? Oh, why? Yeah, that's why, but I don't know why running the I don't know why they're. Or maybe it couldn't compile. Yeah, I see. Because one depends on the other, and it couldn't compile them because I don't know. Oh, I see. The make rule tells it to compile the simple one first, and then the complicated one. And it couldn't compile the simple one because the simple one was running, and it couldn't overwrite the exe file. Okay. Weird. You can't see anything. So how about let's write P A. This is what I had to do before I put the quotes in there, the double quotes in there. So this parse. I think I can do space. I might have to put 20 in there for parsing. So do that again. Start it. That's unfortunate. Oh, okay, I see. Let's do this. Hack.I. You can't do that in the raw assembler. You have to do it in the interpreter. Then, if I'm going to do that, that means I have each one of these has to have a colon in front of it. Okay. So now we will say b4ix and we'll say interpret BIOS. I put it in the BIOS directory for some hack.b4i, and then there we go. Yeah, it's okay. So this is that buffer right there. And then we'll move this down. This is the compiled code treated as ASCII characters, and so for this stuff, and then we should put it back at 100, 100, so that the other assembler can start assembling its code. Yeah, so we only have some of the mess, and I will just hide this. I will move this to like I think it's 800 would be the end of the video memory. That didn't work. It's not 800, it's like C00. Ah. There we go. All right, so now this is the input buffer, and then maybe we'll add another line here that says I'm just going to draw like a little line. That should be a little bit less than halfway across. Just saying where the input buffer ends. Didn't like that. Oh, because I used two Emacs, I will say. Is that right? There we go. Okay, so yeah, so that marks the end of the input buffer. More in there. Is it half one? Yeah, okay. It's 64 by 16, so this is 16 across, so that there should be 4 of them. four lines, fill the whole screen. There we go. All right, so that's the input buffer we're trying to parse. But why does it say parse me here? b4 is written in Pascal, sort of. This interpreter is written in Pascal, and in Free Pascal. I use Free Pascal to compile it. There's also a version in JavaScript. This is written in a language called Lil. There's a program called Decker here, and the scripting language for Decker is Lil. I have an implementation in that. And there's a Godot 4, like GD script 4 for the Godot game engine. And I think that's it. Oh, and J. Language called J. But I mostly use this, the Pascal version, because it's the native code one. In fact, I plan to write a at the what this is building up to is eventually there's going to be a Pascal compiler that runs on this thing, a little Turbo Pascal kind of. I'm calling it Retro Pascal. I originally had the idea like many years ago when I was working in Retroforth, which is my introduction to all this stuff, fourth language stuff. I'm gonna write I just never got to it. But I wrote an implementation of the Ngaro virtual machine that Retroforth 10 used in Pascal, and was gonna complete the loop. Never got around to it. Now they use a different VM, and someone else wrote a different Pascal VM for it. But yeah, that's where I learned this trick too. This little thing when I first read it, Retroforth uses quotations quite a bit, and I read the Retroforth code for this, and it's like it was very confusing to me because it's very well. I don't know. It seemed like it was hard to do. It's not just for assembly language like this. It's for Forth, right? So it's a much more complicated thing. This just creates a label, but that thing has to actually create a dictionary entry in the Forth dictionary, which is just more complicated. And but I spent hours trying to understand these two words in Retroforth, and it's like 2 lines. All right, so all right, we've got our alt thing, this unfortunate extra O in front of it. This is what I was getting at. So ch, I want to have, let's kind of do this test first. I want this function. I want to get the current character, which is just, okay, so the K pointer, the character pointer is going to point at I want that, there's a 0 character there. Maybe I don't want that. Maybe for the input buffer. I'm going to move. So it's be 6, this would be 5ff, and then put 1 pair of dots here and then remove the last one. This is just a hack. This is purely for this demo. I'll need more. It was 1 short to begin with. Retroforth has many language implementations. Yeah, that's what inspired me to write the Pascal one. It was a good learning. I found at the time, that I implemented called Ngaro, Ngaro at the time, was the virtual machine. And I implemented it in Pascal, and it's like this. It had 32 instructions. It uses 4-byte instructions, so each cell is an instruction. And it was very simple, and I learned a whole lot from it. but then he moved on. He kept changing the virtual machines. But then I also I found the low level virtual machine like very easy to understand. And the new one is also I forget what it's called, but it's very simple. In fact, I told he uses 2-letter. His name's Charles Childers or Childers or something like that, CRC, and I uses the same style for his assembler, so that inspired me. 2-character codes or whatever. But for whatever reason, I made my own. Where was I going? Oh, I was going to say that like I found it really easy to understand how to program virtual machine because it was so simple. There were only a handful of opcodes. They all dealt directly with the stack. They were very well documented. But then Retroforth itself, I couldn't figure out where to start, and I couldn't figure out how to understand anything. And it's because Retroforth is written in Retroforth. And it's bootstrapped from like an older version of Retroforth, and like I don't know what it is now, but I couldn't find a beginning. I couldn't find where to start understanding it, and so I at the time it made me realize what I wanted was something that was bootstrapped like from the assembly language and like so on. So that's kind of what I've done, or again, what I'm trying to lay this path. And in the b4 directory, there's a directory called b3a, and this is a simpler version of the b4 assembler written in a smaller version of it, along with a Python assembler that assembles it. So it's a little bit older version of the opcodes and so on, but they're kind of, but it's not this. It's not the py file, it's the org file. And it's like a literate program that shows like how to bootstrap this thing, and it has all the macros, and or it doesn't have the quotes and all that. Oh, it does. Oh, I had quotes before. Wow, I had quotes in this thing, but I didn't have the. I never had them in the Pascal assembly until this morning or yesterday. Interesting, but yeah, and it shows how to implement all this stuff. Anyway, so yeah, Retroforth and Ngaro inspired me to do that, and I wanted to make Pascal on top of it. Hang on one second. My kids just got home. Our family just got home. Okay. All right, so enough rambling about Retroforth. Check it out if you haven't seen it. It's very cool. I was going to write a test. Okay, so the test was make sure that this works. So we have two things, that the current character and the next character. Well, I guess I could have all of these. We'll just go through them. I don't need to put them here, do I? I just need to put them in the test. Sorry, I'm just thinking what to do. I'll just go through what these do, and I'm not going to document them. Or whatever. So this is the input buffer. So in the assembler, I put this label here. So INB caret is the name of wherever this address is. So this is 5FF, right? So if I say INB, I should put 5FF on there. I put this little back quote there. Well, I wanted to have access to that after the assembler was running, because that's not in the virtual machine. It's not stored anywhere in memory. It's just stored in the interpreter. And so I added this other definition. I can say at INB, and now the machine itself can get access to it. And what that's going to do, this is like the interpreter is going to read from this address, and the assembler had already put like that backtick caused it to put that address in there, so that's assembled into memory at that address wherever IND is there. So 5FF is now being read from this slot, whereas here it was being read from an internal label in the assembler. All right, so that's what this is. So at IND is the input buffer address. CH is the current character. So if I have K pointing at this, I would expect it to actually be whatever is at, so what is K right now? K is assembled. So whenever you use like a one character, whenever you use a register name as the thing you're assembling, it sets that register rather than making an internal label. So that actually is available to the machine as a register, and so that's also at 5FF, which is like the 0 right before there. 0 is meant to be the counted string. So this is an input buffer. It's meant to be the the length of the string, and so a string can be up to 256 or 255 characters because the first character is the length. That's how Pascal used to do it in the old days. Turbo Pascal used to do it. Okay, what am I saying? So anyway, K is pointing here, but I don't want K to point there. I want K to point, for our purposes, I'm not using a counted string. I'm just pointing it there. Because this could be some arbitrary text buffer. So K is going to start, put it right. Like that. So now I'm going to restart, and then K will be at 600. Start of that video buffer and at K, say 600, whereas input buffer right, it will be 5, right, because video memory starts at 600. I just didn't want to show that. I didn't want to show this 0 show up as a blank. Okay, so I would expect if K is pointing at that at the start of video memory and that P is there, I would expect that CH, when I invoke CH, it reads, so first it reads the address out of K, puts that on the stack, and then it reads the byte that is at that address. So I would expect the ASCII code for P to show up there. If I say CH, that should show up, and it's 70, and if I say quote P, that should put the same number on the stack. So that's the same. I think so. That's what CH does. So it gets the current character. Next character is also going to put a P on the stack. No, it doesn't. Oh, right. So the next character, what next character does is it reads that address, adds 1 to it, duplicates it, stores 1 copy back in the register, and then reads the byte again. So it reads the next character. I had originally written this as C1 plus K read byte, which is what I think it should be return. But plus K currently gives you the old value instead of the new value. So I think plus K is broken. That's why I want to change it. And I didn't realize that until I wrote this last, or whenever I wrote it. Okay, so instead of that little simple definition, we have this complicated thing. But really, this is just doing, read from that pointer and increment it. That's next character. But then I should be able to do current character again, and then refer to it over and over again without having to type all this out. That's what those two are for. And then LA is just a look ahead. It should return whatever the R is, which I guess would be 7.1. R. Oh, because it's wrong. It says K add, or at K it should be C1 add. Oh no, I see, right? Because I left that ambiguous. Right? Because you could look ahead as many as you want. So if I say C1, or you can just say 1 in LA, now it should say 7.1, 7.2 QR, because yeah. And then if I do 1 out, it should do 7.2 again, but if I do like 2, it should tell me whatever the S is. 2LA. Oh, 2LA. I've already got, where am I? And that's the S. And 3LA should be the E. There we go. And if I say, oh, I can't because I don't have the full bias. All right. I don't think I can clear the screen, can I? Whatever. All right, so that's what look ahead does. And set K back to start just says set it back to the input buffer again, but I probably won't do that because we want it at the next character. Okay, and we don't even need it for this. Okay. So given that we have those, now we can take the character we're looking at and we can now see if it matches. So let's for CH exactly. Let's write the test first. Retest. Okay. Okay. So I want to write a test for CHR. Match exact character. So what should happen is CHR. Really make that a snippet or something. But what we want to do is our grammar is going to be how do we want? So we definitely want to call CHR. Okay, so first of all, we have to have a string to match. So let's put the character pointer at the following string, hi. Hello. And then I want to say, let's just call it, we'll do A and B. So A is going to be I guess we'll load the byte H, call that and return. And then B will be load the byte H and call that and return. Call X or something. Okay. And this should match. Should not. Okay. So CH is first is the H, right? And then K points to the H. K points to the H. So now I want to say A, and then at M, and then show the stack. And I would expect, if we had implemented CHR, I would expect this to show a 1. Right? We're saying this matches. So, and then got that, and then if we do B, I would expect the match bit to be 0. That's what I want. That's the test. Let's make sure the test fails. Test 3. And it fails. And why does it fail? Instead of 1, we got 68, 0. Because 68 is probably the H. Yes, or not 68, 680, 68, X. Okay, so we have to implement CHR to make that. All right, so the signature for this is it's going to take a character and returns nothing. So that's so tests sets match bit to like it's gonna sound weird, but I think this code is gonna be like readable. It is exactly this. At K, no, we want CH, we want to call CH to get the character. Is it equal to the thing on the stack? If so, we're going to put a C1 into M, but else we're going to put a C0 into the M. I'll just move the M out of the end statement. And I'm actually going to, what I did in J and elsewhere is I've used a very tiny function called M0 and M1, which just set that. You know, it's only 2 words here, but the C0 bang of M return, and this should be 1. And is C1 bang M return. So constant 1 M return. If so, 0, else and even this, like we could just call this like M question mark, right? In fact, maybe we don't need this. We just say M question mark. But this would be exactly this, right? So and but it's dot I. So takes a flag on the stack, or flag, and returns nothing. Wait. This is just bang M. Like this is all redundant. Okay. So that's just bang M. I guess technically it like technically if like the number 3 is on the stack, then it's setting it to, and actually I usually use -1, right? It doesn't matter, it's just 1 bit. So it's always 1 bit, and it's always going to be a flag. Oh, I see, because a test is going to return a -1, but I can just make the match bit -1. All right, so let's delete all this, and we'll just put it directly into the M, but then we'll change the test to take a -1. The -1 meaning true. Let's try that again. Oh, I meant to run the test. Unknown word CH. Why does it unknown? Because I am not. Wait, what? because in the tests in the test runner, I didn't include that other file. I don't need the other file. I don't need the input buffer on the screen. That was just a hack. But I do need those functions, and they are usually in the BIOS. But I don't want to load the whole BIOS, so for this demonstration only, I'm going to move. What am I trying to say? I will go to BIOS, take that hack file, and I'm going to take these out of there, put them, delete that, manage my clipboard. Well, I don't need this. I don't need, but these three I want. So yeah, great. So I will just put these in here for now. These should probably be in the BIOS. These copied in BIOS. Okay. So now it should know what CH is, and it should be on the test pass. So this works. That was it. Okay, so we have a passing test for that. Match one character exactly. Okay, but now that we can match one character, I think we're gonna have to change this test in a second, because we don't do the magic escape from we don't do the implicit word that checks the match bit and exits if it's looking for the. We don't do this. This is the old version. Then what he does instead is put something at the start of every word. And I think he just, so this is the BNF parser in fourth, which I put a link to in the chat. BNF is used at the beginning of a production, and that's what, so we don't have this immediate exit. And we're gonna have to put that in explicitly in here. So I'm gonna call that like this is like the sequence operator. So I'm gonna use greater than sign to indicate kind of a little arrow. Like it's the start of a sequence. Maybe I'll put the I'll stick with the O for now. What do we want to do? We say check the match bit, and if it's true, continue, right? So if success is false, so here this is the match bit. If it's false, it causes immediate exit. So we want to say otherwise it saves the scan pointer on the return stack. Oh, we don't have that yet. So return stack. Oh, I see. So then you have to have another one at the end. So maybe we should call it like this. Like that. So, okay, so BNF is used at the beginning of a production. If success is false, it causes an immediate exit. So otherwise it says, so we want the true state. If it saves the scan pointer on the return. So if If it's true, then we're going to read the k and put it, by the way, take it from the data stack, put it on the control stack. Else causes an immediate exit, but not of this function, of the function that we're going to, that's calling it, of the sequence. So we have to put this at the start of every sequence. Maybe I'll use curly braces. Eating friends. And then at the end of it, we have to put the okay. I need to write a test for this. Kind of thinking out loud at the moment. So if the else, okay, and then return. Else is, else it causes an immediate exit, which is so we move the, we're gonna do the same trick again that we did before. Can I do it somewhere else? Oh, maybe I was just demoing. But basically, we want to, you know, the function, the place that says where to return to is on the control stack right now. We're going to drop it. Well, but so is the. Hang on, wait. Causes an immediate exit, but it also. Oh wait, hang on. This is not saying that the okay. This is we're starting a new thing, and we just want to say if we're not matching, then just ignore this because we're skipping over to the next, to the alt, right? So if the match bit is 0, if we're not matching, then we don't do anything. All right, yeah. So okay, right, okay. I was confused because I put this on the control stack. Right. So what we're gonna do is we're gonna exit the calling function, take the control stack, put it on the data stack, and we're gonna zap that and then return. But we don't need to return because it's already on the outside. This is the implementation. Exit caller. If 0 else. If m equals 0, exit caller. Exit caller. Else save. Save the k point, character point. And here we do the same rule. If success is false, stores the scan position. Okay. So at m, if he's saying it backwards from the way that. So if success is false, restores the scan position for the save pointer. Then removes the save pointer from the return. All right, so we're always going to do DC to restore. No, sorry, CD. We're always going to take it from the return stack. Then we're going to inspect memory, or the match. Sorry, inspect the match point bit, and if the match bit is false, and only in that case, store the scan position. Otherwise, we're going to zap it. So if we're matching, we're going to zap it. Else, if the match bit is true, we're going to zap the old k. Else, we're going to put it into k. And then turn. I think that's right. We'll write a test. So if m equals 0, I should really write it like this, right? How I think of it. M save k, else k, else exit caller. If m here, then discard saved, else back. M discard save k, else back. I guess it's exactly what the code says. So that. So this is end sequence. End sequence. Comment is gone. Comment is longer than the code. But so sequence. Oh, we did it. We did do the early exit thing here for alt. But we prep by saving the character pointer, and we always exit if the match bit is 0. But this is really the start of any rule. Put this on it. We will wrap every rule with C. Okay. It's a little more complicated because it's I don't know. I'm not sure why he needs 4 words for this. Oh, because he's also giving them names so that he can call them in the dictionary. We haven't gotten that far yet. In fact, we're going to use the assembler's dictionary, but we're going to have a problem with forward references at some point, and I don't have an answer for that. And I think what the answer is going to be is that when I define something, I'm going to have a syntax for like defining forward reference, that little slash or something. I haven't decided that yet. What I've done in the past is I've just named a register. And so anytime I have a recursive, like, you know, 2 mutually recursive functions, I have to give one of them like a register to use. And then I invoke it through the register. But then you can't use that register ever. That's part you mean, as long as you're using that program. So probably not. Okay, I think this works. So let's test it. So sequence. I think this is kind of like the more primitive thing, so I'm going to put that first, even though we didn't do it first. Because all we're doing is the match bit. Alt is going to be. In fact, I'll even do sequence. Maybe I should have started with that. Or rather, not a O. I might have some more work to do on this. So let's see. All right, we're going to assemble a new grammar or whatever. What do I want to match? Let's say I want to match ABC. So usually when I do this, because of this problem, right? So now, right now, in order to match ABC, I have to write load byte A CHR, load byte B CHR. Right. So okay. So what I'm getting at is, sorry, I'm thinking of three things in my head right now. So I think I call this string or lit. I call it lit. Match a literal string, and it's to save you from having to write a sequence of characters like this. And it's just a shorthand. This is and we can put annotation. This is to save you from having to write a sequence of CHR operations. And so this is to match an entire string. To do match say read.lit. Here we will say A is hello. And now A would be I guess we'd put the whole string on, the whole thing on the stack. Which here you'd put a counted string. You would say hello. Lit. Return. And here you'd say match. How about nope? Yeah, I'll call these yes and no. Same here. These tests for all these tests. Vertical. So yes and no. In fact, I think all these tests are going to be the same, at least for the simple stuff. But we also do want to put this here. We want to put it somewhere in memory so we can refer to it, and we want to see what the where K is at the end of this match. Right? So really, that's annoying. I don't have any way to say save where we are and come back to, do I? I think I can say that, but I don't want to. How about we put an S here? So then we say, so S and K will both be pointing at that. They both point to the same place. Then we will put K back at the start of the string. At S, put K. Put K. Okay. This is messy. I mean, just messy to test it all. Like, I might need like some little macro or something to set this up. Because I also need to set, I haven't done it yet, but I'm going to need to have to set the match bit to 1 at the very start. I need like an init parser kind of thing. And then, so let's, so this should match, and then it should match, and let's also say what is A S of, what's the distance? How about we call this length? Maybe this is a primitive that we, ln is, but it's not a primitive, I don't know. Alright, so then we'll say length. So I would expect this to match 2 characters. Copy this to the, very messy. I don't have a way to say like run the same thing on the start of every test yet. There's no setup kind of, except in whatever you choose to test run. Same thing here. This needs to be a function. I need to be able to write a test for this, right? To be able to write macros for tests now. Maybe I'll just make a little harness function. Purpose of testing. I don't know. But now I'll just copy and paste and say length here. So run it, get the match bit and the length. And this should consume 1 character. It is so much. I need a function, like a macro or something. And same thing here, length. So we use apps, yeah, like. And the length should be 0 here. I think I've broken, like, I don't think this test will pass anymore. I don't have the, because it's not incrementing k. So CHR should increment k. Match and inc. Okay. We go back to the other file. Tests. Test implementation. Character and k. Then duplicate it, and then if so, C1 plus k that. Not then, sorry. Match share inc k and k plus plus. Or it's plus plus k, and it should be k plus plus. Okay. K. All right, so now I think that test will pass, and it'll fail the next step. Did it? BCHR. It says -1 because I put these in reverse order. You want to take k and subtract s to see how far I moved. All right, so that test failed. So CHR passed now. We got 1 dot, and then lit failed, which I expected because I haven't implemented lit yet. It is 10:47 here. I'm probably going to wrap this up and continue this tomorrow. Got to put my kids to bed. I'll put a little thought into like how to make these tests easier to read. We haven't gotten to this part yet. I think this implementation works, but like I don't know how to write the test here yet. But yeah, thanks for watching. It's nice to have an audience. I usually talk to an empty room. Let me know if you're on the concatenative server. Give me a link to your uninstall implementation if you did anything. I'd love to see it. Maybe you can. Maybe I can learn from you. You're doing. Figure out what I'm breaking. Anyway, thanks for watching, and I really appreciate it. And I will. Hopefully for everyone else, I'll see you again soon. And yeah, I'll get this onto the b4 site, and everybody can check it out, right? Or the GitHub site. Thanks for watching, and I'll see you again.